a smaller than normal lecture today. I know you guys are really tired. Today's lecture is going to be the continuation of heat transfer, and because we had technical difficulties on Wednesday, some of the slides are a little bit of a refresher just to get you on track as to where we left off on the board. And we're going to wrap up the remainder of the heat transfer section so that on Wednesday's class we can devote it entirely to these analogies between momentum transfer, mass transfer, and heat transfer. And there's actually some formalization of these analogies so that you can easily flip back and forth between all three of them. So we're going to dedicate Wednesday's class to that, which means today's class we have to pretty much get through all of the rest of heat transfer. And as I've told you, everything you've learned up to this point for mass transfer is almost entirely applicable to this last section of the class, which is why we're able to go through it so rapidly, because we're really just substituting in new parameters, new variables, but the methodologies are entirely the same. The mathematical operations are the same. And so the fundamental difference between these is that we have energy instead of mass. So when we're transferring energy instead of mass, we have the analogous diffusion fixed first law. We have the analogous convection with the convective mass transfer. But then we have this third form of heat transfer where there is no analogy with mass transfer, and that's radiation. And in last class, we didn't get far enough along to just tell you what that definition is. But I mentioned the Stefan-Boltzmann law. So in the case of heat flux, Q over A for radiative heat transfer, there is a coefficient, sigma, which is predefined, which allows you to consider heat flux as a function of temperature to the fourth power. Okay? So that's just for your own knowledge. I think in Dr. Ethier's lecture notes, he says you won't even have to use this for the remainder of the class. There are, I don't think there are any examples in the practice problems I gave you, but there are times where you can tack on radiation as an additional mode of heat transfer if you're looking at things in terms of resistances in series. So as long as you have an analogous definition of Q over A, you can consider that, that heat transfer for an additional mode of resistance there. So we're going to really focus on convection and conduction. And with these, we defined a thermal conductivity, K, which is different from the Ks we've used elsewhere in the class. So this is not a kinetic chemical reaction term. This is not a convective mass transfer term. This is a conductivity term. So I know there are a lot of Ks in this class. Just make sure you understand what the symbol is for this one. It's defined in terms of watts per meter Kelvin. And by this point in the class, you should recognize that a gradient of T is very different from a delta T, right? Gradient T, you can substitute in a partial derivative with respect to x, y, z, r theta z, r theta phi, depending on your coordinate system. And so you would have a dt dx, for example, here. Whereas a delta T is just saying a differential in temperature. And you're basically eliminating that length scale by the units in your convective heat transfer coefficient with meters square in the denominator. Okay? So we started to go through this last class, and I just want to reinforce this a little bit further. Because this is what I was doing on the board with two things in series where we have different thermal conductivity associated with the material. And we said that you could think of this as a sum of resistances. And so if we have our delta T, which spans from T1 all the way to T3, you can equate the Q over A here with the Q over A. Let me actually... right here versus right here versus right here, right? But if you're equating those Q over A's together, you wind up with a summation of the series in the denominator, which is just that distance spanned divided by the K1 plus the distance span for the second section divided by the K2. And this is what we explored in the flipped session with our practice problem. Okay, so if we want to consider convection off the second material, because we have Q over A equaling H delta T, it turns out that if we think of 1 over H now as our convective resistance, then we can add that in to the summation in the denominator. So now if this is, for example, we have glass and we have metal and then we have air going out to some ambient temperature T4 being T infinity, some distance away, we can think about this as an additional resistance term. And usually it's pretty small, right? So most of your heat transfer is occurring through the conductivity, but then you can have this additional term where you have basically a skimming off of that air layer from the surface, which is adding an additional resistance. Okay? So if you do the unit balance here, you'll see that your 1 over H will work out with your delta X over K1 or delta X over K2, so that everything you're adding here is unit consistent, such that then this all balances out okay. And you could come up with this on your own by taking that Q over A being equivalent at each interface and equating them and solving for this. But this shows you an example of how you can do that. Okay, so last class, we had this messy control volume formulation, which I was trying to do on the board using my cell phone, trying to describe to you from the first law of thermodynamics how the conservation of energy is considering the heat, the addition of heat into the system, minus the work done by the fluid on the system. And so we said that work term was really called a shaft work. And that may be, the fluid actually pushing a propeller or something like that in the system. And then we had our Reynolds theorem, which we could derive with respect to our variable E as our system variable, which allowed us to come up with this formulation, which considered the change across that control volume of our element and what was happening inside that control volume, as well as what's coming in and out of the system at the controlled surface. And then we had this additional viscosity work term that we had to factor in. Okay, so this was really considering the energy in the form of heat capacity. It was thinking about it in terms of potential energy with gravitational term and kinetic energy in terms of our velocity squared term. So we're probably never going to have to actually use this equation for problem solving in this class. But as you've seen throughout this class, we go from a control volume perspective into a differential form. So we started out, before we got to Navier-Stokes, we started out doing momentum transfer this way, right? And we flipped it into a differential form, which was much more compact and easier to work with to get to Navier-Stokes. Here, we're also going to move into a differential form, only now we're going to be considering this differential energy equation. So this is the all-encompassing equation that describes heat transfer as a function of time and location. So with this, we can consider a substantial derivative of temperature, and we can consider, if you pull the K out of this, then we've got a Laplacian term here. So that's oftentimes pulled out just like our diffusion coefficient was pulled out. We've got an exothermic or endothermic reaction term within the volume, because just like chemical reactions that produced or consumed our molecular species of interest, now we've got chemical reactions which can produce or consume heat, right? Oftentimes we think of chemical reactions generating heat. A lot of times that's the case in biological systems. But there are also examples of endothermic reactions that consume heat as well. And then there's also this dissipation function. Dr. Ethier includes this in his lecture notes. For all intents and purposes in this class, we can ignore this particular phi term, but for complete correctness, that should be included as well. So what we're going to be doing is rearranging these terms a little bit, and that allows us to think of this thermal conductivity K divided by the density of the material and the specific heat capacity of the material, C sub P, as a new parameter, alpha. And this alpha term is going to represent our thermal diffusivity. So this is something that's a little bit different from mass transfer, where we use diffusion coefficient everywhere. Whenever we wanted to describe molecular movement, we had that D, and that D was everything we needed. Here, we need to account for different material properties such that we're taking into account the fact that our density changes at different temperatures. Specific heat capacity is something that's consistent. It's a defined property of the material of interest. And our thermal conductivity, which can also change as well. That's why it's actually inside that divergence term on the upper equation. So by taking into account the conductivity, the density, and the specific heat capacity of your system of interest, this new alpha term in this particular form for this equation will then be representing our analogous diffusion coefficient. So I don't think yes, I do have a final form here. So if we rewrite this into a form that's more familiar to you, we can consider this substantial derivative here. And we can say, okay, if we're ignoring the field effects so that our velocity isn't changing as a function of x, y, and z, and we just consider this change as a function of time, then that partial derivative, I'm kind of flipping this around, so we're going to the left-hand side here. Our partial derivative with respect to time is going to be on our left-hand side. Our alpha term is going to be like our diffusion coefficient. Then we've got our Laplacian of temperature. And then what we've done here is we've just taken the remainder of these parameters and we've divided through to make this one analogous R sub A, right? So now you have some, if you use the PDU toolbox language, volume source, right? And this volume source now is going to be an endothermic or exothermic reaction, so it plus or minus, depending on if it's being added in or taken out of the system. And then we're just dividing through by our rho Cp here. Okay? So now you can see that this is so much like our dc dt equaling our d Laplacian of c plus Ra. Right? And so everything you've done up to this point in this class, where you've been able to solve for a concentration profile, you've been able to solve for a concentration at a particular location, you've been able to solve for a flux at a particular location, all of that can be applied using this constant K, no fluid motion version of your differential energy equation. All right? So just to walk you through an example, and I'm going to go through this fast because you've seen cylindrical geometry before, you've seen how to do this integration before, but just to kind of walk you through, again, if we're starting with an alpha Laplacian of t, and we switch it into cylindrical coordinate systems, and we basically cancel this out because it's being divided through onto the left-hand side, then you wind up with the same mathematical form that you had from your cylindrical steady-state diffusion problems. Okay, so it winds up that your solution here is going to be initially independent of your diffusion, your thermal diffusivity here. Now, depending on the boundary conditions, it may factor back in later on, but this is just the same mathematical formulation that you've seen so far. So if we say that for this cylindrical blood vessel, if we're just looking at the temperature profile through the thickness of that vessel wall, then we've got a constant source of heat from the blood, which is maintaining that at 37 C. So that's going to be our T interior, and that's going to be the interior radius of that curved vessel wall. So that's going to be a defined temperature at a defined location. So we can use that as our boundary condition and plug that in to solve for one of our integration coefficients. If we say that we have some knowledge about the temperature at the outer radius, then we can solve for that second integration coefficient. So plugging that in, solving for A, we have everything in terms of our T out and our T in, our R out and our R in. And plugging it all in together, we get some temperature profile that's a function of R. So this is really T sub R here. Okay, so what we've done is we've just done exactly what we did for our steady state 1D diffusion problems, only now we've done it in terms of temperature. We've swapped out our variables of interest, and we didn't even need our thermal diffusivity in this case. Okay? So you guys are ready to take on steady state heat transfer, right? This is straightforward. Okay, it turns out you can do unsteady heat transfer as well. So on a single slide, I've got everything you need to know for unsteady heat transfer. We've got different ways in which we could do this. We've got our charts. So if we're doing our charts, our unaccomplished temperature change now is our Y is being replaced with T's instead of C's. So we have a T infinity, a T naught, and the T distance we're interested in within our control volume. We've got our relative time. And this relative time then is going to be a function of alpha, T, and the overall size of our geometry. And if we want to substitute in our K over rho Cp for alpha, we can do that, depending on what information we have about our property. And then we've got our relative position. And now our relative distance, remember, this is really kind of like conduction over convection. And so now our conduction over convection is our thermal conductivity versus our thermal convection. And so, in fact, if you go through your charts in the back of the book, I think most of them actually use the heat symbols instead of the mass transfer symbols in their legends. Maybe not all of them, but it's more common for it to be expressed in terms of temperature instead of mass transfer. Okay, so that's one way in which you can handle unsteady heat transfer. And remember, for the charts, you're considering what's happening inside a defined geometry. So you're looking at a ball, you're looking at a slab, or you're looking at a cylinder, and you're asking what's happening inside that ball, slab, or cylinder. And you're looking for some time-dependent change in how that either that mass or that heat is being transferred within that control volume. Now, it turns out that we have different ways of handling that remember, if we have a very small BO number, we can use a lumped parameter analysis. And this is kind of a shortcut method. So we recommended always calculating the BO number first to see if you can just apply this, this equation alone to solve for your unaccomplished temperature change. Or you could solve for T if you wanted to solve for T. But this was pretty much a shortcut method where you don't have to rely on charts and the approximation of the charts if we have a very small BO number. So now, substituting in, instead of concentration, we have temperature. Now we've got our thermal convection term here, and we've got our rho Cp term here. So that's being introduced here. Okay, the third method in which we can approximate changes as a function of time is with the semi-infinite approximation. And so the semi-infinite approximation is assuming that you have an instantaneous change at a surface, and you're assuming that the time and the length scales of what you're examining are so large that you're going to have a very small profile change near the surface that's going to be negligible far away. So at that infinity value, it's going to not change as a function of time, so such that only very local changes are going to be a function of time near the surface. So we can substitute in our temperature and our alpha term here, and of course you could substitute in your K over rho Cp for alpha as well. And remember that this was analogous to our x over 2 square root of d, our diffusion coefficient, times t. And this also gave you a formulation for a very easy solution for flux. And I didn't write that equation on here, but that flux is a function of pi, d, and t for the mass transfer situation. Okay. So again, any of the unsteady problems that you were doing for mass transfer, you have the ability to then be doing this for heat transfer. Okay? And I gave you a bunch of extra problems that I put in the problem set folder so that you can practice these beyond just what was in the problem set 9. So there are tons of unsteady heat problems to work through. So I came across last week a textbook example that I thought was so nice, and it made me pine for a really great biotransport textbook that would use these types of analogies to distill down some of what we teach you. But this particular textbook on heat transfer gave this really nice analogy on the significance of the BO number. So they said, okay, pretend that volume of interest that you're looking at, whether it's a stainless steel ball bearing or it's some gel slab you're looking at or whatever, pretend that it's like an island. And you have boats that can come up to your island and let out passengers. And then you have a bus system, which is moving people around the island to disperse them. And it was saying that basically if you use this analogy, you can think about, okay, if you have a really lousy bus system, then you're going to have overcrowding on the shores because people can get to that island, but then once they're dropped off, they have nowhere to go. And so the BO number is like, a large BO number is like overcrowding at the shore where you have inefficient conduction. So you're going to wind up with a situation where you have a great convection in which things are allowed to get to that island, and then poor conduction, inefficient conductivity or diffusion, where then they're not being efficiently transported to the interior of the island. So I thought that was a really nice way to think about it because it helps kind of imagine that balance between different forms of transfer and what's most efficiently here. And they also said something that I think is worth noting here, that the surface has zero thickness. And so this surface itself is not storing any energy, and the heat reaching the surface of a body by convection must continue its journey within the body by conduction. So once it reaches there, it's not like it's going to stop and everyone's going to hang out on the beach, right? They've got to continue their journey inward. And that surface itself is not a place where that heat is going to be stored. It's just the interface between the modes of transfer that are occurring, or transport. Does that help a little bit for you guys? Yeah? Okay. I feel like I should be like mining textbooks for these analogies, because I thought this one was really illustrative. Oh, and I also love this. They say we've disregarded radiation and thus air traffic to the island. Okay, so we've got this new parameter, alpha, which we're using to represent the thermal diffusivity. So we're moving into pi groups now. With momentum transfer, we consider that viscosity term mu, which is mu over rho, which is representing our momentum diffusivity. So guess what? We're going to be relating these two together. So we've got the same dimensions, L squared over T, and we're going to define a new pi group, Prandtl number. And the Prandtl number is going to represent the ratio of molecular diffusivity of momentum to the molecular diffusivity of heat. So we can define this the same way we defined a Schmidt number. Remember, the Schmidt number was considering momentum diffusivity versus molecular diffusivity. Now we're defining this Prandtl number, which is the analogous situation for heat transfer. So do you guys remember what we did with that Schmidt number? What was it useful for doing? That SC value, when were we calculating that? No ideas? Yeah, it was for the Sherwood number. So remember, if our SC value was equal to 1, then we had a reduced form of our Sherwood number, which was just a function really of the Reynolds number and this messy coefficient in front. And then when the SC was not equal to 1, we raised the SC to the 1/3 power. We included it in that calculation of the Sherwood number. And we were allowed to do all sorts of things. We could solve for a convective mass transfer coefficient at a particular location. We could do integration across our plane of interest and come up with this average convective mass transfer coefficient. We had all these cool things we could do with it, right? So we're going to do the same thing with the Prandtl number, which means we need an analogous pi group to the Sherwood number. One thing just to mention, because the Prandtl number is a combination of fluid properties, it's thought itself as a property of the fluid. Okay, so we've got another pi group here. It's called the Nusselt number. And you'll see the Nusselt number here is denoted with a little L. That means it's defined for a particular location, such that we've got our convective heat transfer coefficient H. We've got our K value, which is our thermal conductance. And we've got some distance at which we're evaluating this. And just to remind you, our Sherwood number was defining this for our K sub C, or to be consistent with the lecture notes, this was an F, right? A distance x that we were interested in our diffusion coefficient. So this is exactly what I was talking about. If our diffusivity is totally equivalent between momentum and mass, and our boundary layers were identical, then this would wind up being equal to 1 and just drop out. Our Sherwood number here is going to be defined, our Nusselt number is going to be defined in the same way and used the same way that we use the Sherwood number. So our Nusselt number then can be a function of the Prandtl number and the Reynolds number, in the same way that our Sherwood number is a function of the Schmidt number and the Reynolds number. So guess what? That table, that chart I had in the lecture slides, which went through all the geometries and all the calculations with those ugly formulas for how you would go about solving for K sub f, or average K sub f as a function of the Sherwood number, we can use those same formulas and substitute in Prandtl and Nusselt to calculate any kind of h for a particular location or an h bar of interest. Okay? So even though these aren't given to you explicitly, you should be familiar with how you would go about solving for something like this, because it's completely analogous. Okay. So I know some of this material is kind of like, why would I ever want a ratio of thermal diffusivity? Some of these are actually used in real-life situations. And so I always like to dig in the literature and try to find an example for you guys so you know why someone would want to calculate this. So there actually is an application where they're using a catheter to ablate tissue in the myocardium by applying a high-frequency current with a little electrode. So if you have cardiac arrhythmia and you have misfiring of some of your pacemaker cells in the cardiac tissue, you can actually zap a little location of it and change those spiral, electrochemical waves that form by basically perturbing the geometry of those firing cells. So the goal then is to come up with a catheter that can wind its way into the heart, zap a location with this high-frequency current, thermally ablate the tissue, and then correct the arrhythmia. So if you're going to do that, you really want to know what kind of heat you're transferring to the tissue. Too much heat, and you'll get too large a spot of dead tissue. Too little heat, and you don't really get effective correction of what you're trying to do here. So the rationale is that we're going to want to short circuit these electrical signals. The question is, what is the thermal energy being delivered to that site within the heart? The complication is that the blood flow is causing convective heat loss. So you want to zap something and apply heat, but you have this constant, you can't stop the heart, so you're going to have this constant swishing of fluid past that location. You've got a local convective heat transfer coefficient, H, that you want to get. And you know that your in vivo values vary widely. So a sensor was developed for calculating H for different flow rates. Now, if they're going to calculate this, they're going to want to use the Nusselt number, which means they need the Prandtl number and the Reynolds number, right? So this particular paper, they came up with a circulation system. And for some of you that have worked ahead on some of your practice finals, you'll see this figure actually showed up in one of the finals. I think it was from last spring, where I built upon this idea for a test question. So they've got a pump system where they're going to have circulating flow here. They're going to maintain the fluid bath at a constant temperature. And they've got this exposed sensor area that they have a known geometry associated with it. And then they've got this sensor at the tip of the catheter that they're trying to use to measure this thermal exchange. So the idea is, if we can't do this, if we can't measure this in vivo, let's build a system so we can characterize that sensor in vitro, or ex vivo, I guess. And then we have knowledge of what we're doing once we're inside the heart. So the beauty of this is, right, if you're controlling the circulation here, you can manipulate that Reynolds number. So you can just jack up the fluid velocity and alter the Reynolds number. So that's something you have control over. What they don't know is other characteristics of the sensor, and that's what they wanted to establish. So the tube is more than 20 times longer than it is wide, and this 20 millimeter inner diameter is such that we can assume that the laminar flow is fully developed. And because it's a cylindrical geometry, we're going to have to use the characteristic length of our diameter instead of some distance traveled in like a planar dimension, right? So if you remember those charts that we had, they had separate equations associated for pipe flow versus flat plate flow. And the characteristic length we've seen throughout this class has been either distance x traveled, or for cylindrical geometry, something in the radial dimension, usually diameter. So here, the criteria for laminar flow is going to be a Reynolds number less than 1,000. Okay? All right. So how can we solve for this average heat transfer coefficient? We can solve for it if we know the average Nusselt number. So we can solve for the average Nusselt number if we have knowledge about the Reynolds number and the Prandtl number. So what have I done here? I've looked at the equation for Nusselt number here. I've defined it for a particular location that we're traveling. And we can then look at what parameters are needed for this. So in terms of the Reynolds number, we need knowledge about our V infinity, our density, our viscosity of the fluid, and the characteristic length of interest. Our Prandtl number is a function of our viscosity, our heat capacity, and our thermal conductivity. Okay, to solve for the Prandtl number at 39 degrees, they use the following values. They've got a density of 992.47 kilograms per meter cubed. They've got knowledge about the viscosity in terms of newtons times second per meter squared. The specific heat capacity, and this is something maybe I should go into a little more detail, that C sub P value is really defining how much that material can absorb of heat. How much can it store? And so that's an intrinsic property of the material of interest. So that's in joules per kilogram Kelvin. And really, the way that they like to define this is how much energy does it take to jack up the material by 1 degree Kelvin? Okay, and so that's kind of, when you see the units, that kind of makes sense, right? It's joules, it's energy being applied versus kilograms, so it's per unit mass per Kelvin. So it's saying, in order to raise that 1 degree, I need how many joules in order to do that. And then our thermal conductivity, we've seen over and over again, is going to be watts per meter Kelvin. Okay? So if they have that information, they then can calculate the Prandtl number. And if they have the Prandtl number and they can manipulate the Reynolds number, then they can decide, okay, this is what this means in terms of what that Nusselt number value will be, and therefore what that convective heat transfer coefficient is going to be. All right? So that's how we would go about using that kind of information in a real biological context. So what I've been doing so far is I've been trying to adhere fairly closely to Dr. Ethier's lecture notes for Unit 6 on heat transfer. And one thing he has in that section, which he has listed as independent student reading, is the whole derivation of the differential energy equation. That is something that I figured that you can do on your own. You can go from the control volume form to that differential energy equation form. And instead, I just gave that to you just from one slide to the next without going into any detail. So all of that information is in those PDF lecture notes if you want to look at those. So next lecture, what we're going to do is we're going to then, all of these analogies that I've been trying to highlight throughout this lecture, we're going to then put this in a more formal definition. So there's something called the Chilton-Colburn analogies. And if you actually look at sort of the objectives of this class, a primary objective is that you can be able to relate these different modes of transport to one another. So we're going to be talking about how you can use those relationships. So say I know nothing about the convective heat transfer here, but I have knowledge about the mass transfer. Well, there's actually a way that I could go about getting H if I have some information about K sub F. And that, I think, is a really, really cool feature of all the material we've been describing, because it says that you don't even have to measure anything related to heat in order to figure out how heat would behave in a system. All you would have to know is something about the molecular motion, and vice versa. Say, where it's oftentimes really a lot easier to measure temperature than it is concentration in a biological system. Temperature has great electrodes, right? They're nice thermistors that are out there that can detect very, very sensitively very small temperature changes. It's really, really hard to measure different molecules and concentrations because, of course, it depends on the type of molecule and what kind of analytical method you can use to detect that molecule. If it's a protein, it's different than if it's an ion, right? But if you've got information about heat, and heat flow, and the respective temperature changes, then you can make those mass transfer calculations. And so to me, that's like the coolest thing. And I hope you guys can see that that's sort of the beauty of this class is we've built up all these different things, and now you can put them all together, and you can see how knowledge about one will help you find information about the other. So I think that might be my last, this is my last slide. So I finished a little bit early today. I want to mention to the class that last Friday was our last flip session. We'll be in this room on Friday, and we're going to have just an overarching, all-purpose review. I'll try to highlight material I think is really important for the final. The final has been written. I know what's going to be on it. I'm not going to give you everything, but I will try to winnow a little bit on what you need to know for the test. Wednesday's recitation. In Wednesday's recitation, I've asked the TAs to just be prepared to answer questions about the homework. So problem sets 1 through 9. Any lingering questions you have. Remember, the final's on Monday, so you don't have a ton of time to study. So start looking over the material from the entire course and come into the recitations prepared with questions you want answered. Because rather than going through a practice problem, they're there to basically just field lingering issues you have about the material. Yes?
Do you know when the assignments should be graded by?
So we're trying really hard to get those done. We will definitely have them to you sometime this week. The MATLAB assignment, I know, is going a little bit slower than planned. I'm going to help Jackson grade them so that we can get them back faster to you. And the quizzes you'll either have in recitation on Wednesday or I'll bring them to lecture on Friday. It's tough because our graders are all like you. You know, they have massive assignments due at the end of the term, so we're trying to work with them to get them back. You will definitely have all the information about your other grades before you go into the final, so you know where you are with respect to everything, okay?